Hello, we are Solar Tracker Group 8, and our vision is to reduce the impacts caused by the built environment using PV solar trackers. For our problem statement, most of the buildings are not well designed to manage the inner temperatures, and also most of the existing buildings don't produce any electricity, meaning that a lot of potential is lost. Our design vision then is to create a PV solar tracker that follows the sun throughout the day and the year, targeting to maximize the energy gains and acting as a partial shading device. For the criteria, we focus on the applicability on existing buildings with the lowest environmental impact, and also a system that could be controlled through a computer system to make it more efficient. As we recognize that the main topic is the solar tracker, for our infographic we decided to evaluate the best rotational degree for the solar panels in order to produce the most amount of energy during the year. First step would be to pick up a location and also the orientation of your building and your facade, and also the shape of your panels. After modeling and calibrating the parameters, you can run the simulation and then analyze the best rotational degree for the panels. For our product, after running some tests, we concluded that the dual axis is the one that has the highest score for energy generation, and we decided to follow with it. Combining to that, as a process of evaluation, we tested different positions on the facade, grids, and formats for the panels, and then we select the hexagonal one, which responded as the best option for the rotational axis and shading. During the building weeks, we made a lot of mock-ups to test all the mechanisms in order to make the panels move the way they should. This is for the x-axis, and this is for the y-axis. Our final product is a set of hexagonal panels forming an array. With this shape and this grid, we were able to maximize the gains and also protect the building managing the heat load. As you can see in this section, that at the same time we generate energy, we protect the building. On our device, we have two operations, and for them, we had to create different mechanisms. First is the daily operation. In order to follow the sun throughout the day, we came up with this solution, which is a frame of movable parts connected to a pump. When the pump goes back and forth, the movement is translated to the rods, and then the whole set moves in the x-axis. The second operation is the annual. Along the year, we have different seasons and then different angles. Our panels must be able to respond to it. For this one, we created a set of pulleys and a belt system that goes along the rod, and on the top of it we have a motor, and then when the motor is activated, it twists the pulleys and the belt, and all the set moves at the same time, producing the y-axis. Finally, when we combine both movements, we have the seasonal and the daily movement on the same structure. This is our final design during the building weeks. Here we can see some important parts such as the universal joint that translates the x-axis movement, and here the structure we call the neck with the set of pulleys, and here the final design. Another important part on our design was the structure. To connect our product with existing buildings, we had to create a flexible rebar that it's adjustable and can be flexible depending on the type of structure. If it's steel or timber, we have different joints. Here we have some renders that illustrate a bit of different options. Then finally, for our reflection, we start off by defining a clear problem statement and the criteria to focus everyone to develop one design. At the end, everyone has produced and we came out with a myriad of design solutions to tackle our problem statement. And this This huge amount of ideas put us a bit behind of the schedule because we took too long to evaluate and chose one option amongst all of them. To get back on track, we decided to make a series of schedules and tables in order to compare all the designs that we came up with, and then it kind of helped to shorten our list. And then we went to the building weeks with a couple of options, and then we could test out them, making models, mock-ups, and then testing out the mechanisms. That was actually quite helpful because we could see how the mechanisms they really worked, and then it helped to shorten the list even more. And then at the end we combined the best solutions in one final design. Data is still lacking to understand the energy consumption and overall efficiency of our product, and for that we would need more resources to get these questions answered. And this is the end of our presentation. Thank you everyone.